The last topic in the chapter is the wave-particle duality. The idea of the wave-particle duality just come from Louis de Broglie in the 1923. Okay, so he thought that if the wave, such as the electromagnetic wave, right? If the wave can behave as the particle, actually let me just write clearly. Okay, if the electromagnetic wave behave as the particle, which is just called the photon, right? Then he thought that the real particle, all the physical particle, okay, the physical particle, okay, should behave as a wave as well. Okay, so it means that the particles will have some property of the wave. Okay, so this is called the matter wave. Okay, just called the matter wave. It means that the particle will show some property of the wave. For example, it can have the interference. Okay, it can have the interference, and it can have such as the diffraction. Okay, for example. Okay, if the momentum of the physical particle is p, okay, if the momentum of the physical particle is p, right, then we can get the wavelength of the matter wave to be the lambda. Okay, so now if we look at this equation of Einstein, right, we said that the p equal to the h over the lambda. So if we move lambda to the left and then p to the right, then we can get that the wavelength, okay, let me just write here, the wavelength of the matter wave is, okay, so we can get lambda equal to the h and then over the p, right, or just equal to the h and then over the gamma times the m and then times the v. So don't forget that this is the relativistic momentum, right, of the particle. Okay, but now if the particle move with a slow speed, okay, so it will be in the non-relativistic motion, so the gamma equal to the 1. Okay, so that's why we can get that this equal to the mv. Okay, but now let me just write in the general case that we have the relativistic motion, then the gamma is significant. Okay, but now the question is, so why don't we see any the wave property in the real object, right? The object that we get used to. Okay, so let's consider, for example, okay, for example, okay, if we consider a student, okay, if we consider a student, okay, moves, run, okay, let's say run, is, no wait, sorry, of mass, I don't know, maybe 60 kilogram, okay, is running, okay, with the speed of, I don't know, maybe 2.0, let's say 2.0 meter per second. Okay, so now we just want to find the momentum, we just want to find the wavelength of the matter wave, right, of this student. So let's say that the lambda, right, the wavelength equal to the h and then over, okay, let me just put in a number. The h is the 6.626 times 10 to the negative 34, okay, and then over okay, now the speed here is very low, right, compared to the speed of the light in vacuum. It means that the gamma here is just about 1. So we have momentum equal to the mass and then times the velocity. The mass is the 60 kilogram and the speed is the 2.0. Okay, so then here we can get that okay, right, and then over 120, right, because it's 60 times 2, so just equal to about here, okay, 10 to the negative 36. Okay, so it's just about 10 to the negative 36 meter. So now you can see that this value is what? This value is very small. Okay, it's just very small. So it's, I mean, we cannot detect this, I mean, very small value here. No, actually it's, I'm sorry, again, it must be meter. Okay, but still it's just really small, right? But now let's consider another example. Okay, so let's consider an electron. Okay, moves with the speed of, okay, so let's say just about 10 to the 7th meter per second. Okay, if we consider an electron moving with the speed of 10 to the 7 meter per second, so is the speed large compared to the speed of the light? Actually it's not, right? It's not, because we say that to use the relativistic equation, okay, to use the relativistic equation, the speed of the particle v must be in this region, okay, from the 0.3 times the c. So what is the 0.3 times the c? Okay, so c is about 3 times 10 to the 8, right? And then times the 0.3 is just about the 0.9 times 10 to the 8, okay, or it's just about 10 to the 8 meter per second. Okay, so it means that if the speed of the particle is in between 10 to the 8 meter per second to 3 times 10 to the 8 meter per second, so then we can use the relativistic momentum. Okay, but now in this case we just have the speed equal to the 10 to the 7 meter per second, so we can just use m times v as usual, right? So then we have, okay, the lambda equal to what? Equal to the 6.626 times 10 to the negative 34, and then over, okay, now the mass of the electron, right? 9.109 times 10 to the negative 31, and then times the speed, right? About 10 to the 7, okay? So it's just about, let's see, so here, okay, and then over, and then times 10 to the 7, okay, it's just about 10 to the negative 11 meter. Okay, it's just about 10 to the negative 11 meter. So which type of the electromagnetic wave having this wavelength? Remember, which type of the electromagnetic wave having this wavelength? It's just the X-ray, right? It's just the X-ray. So it means that electron can behave as the X-ray. Okay, electron can behave as the X-ray, and this wavelength is detectable. Okay, so let's look at this picture. Okay, so this picture just come from the Bosolid. Okay, diffraction, interference by the Bosolid. It means that, okay, let me just draw a picture first. It means that if we have the Bosolid here, and then Okay, so we have the buzzer lead, and then we have the screen on this side. Okay, so this will be the screen. Actually, it should be black. Oops. Okay, we have the screen, right? And then if we have a beam of electrons, right, from the left hand side, so let's say that this will be the beam of electron. Okay, so we have the beam of electron, right, just moving to the right hand side, and then passing through the buzzer list here. Okay, and etc. So let me just draw only this arrow. Okay, and okay, so this is the experimental results. If number of electrons are small, okay, so we just see nothing. Okay, so the white dot line here just mean that the position that electron is then on the screen. Okay, so we have the black screen here. But then if we increase the number of the electrons more and more and more and more, right, it's gonna look like this. Okay, remember what is this one? It's just the interference pattern, right? It's just the interference pattern, okay, of the matter wave or just the electron wave. It's just the same as when we have the visible light passing through the buzzer lead, right? And we can see this type of the pattern as well. Okay, so let's look at this one, right? Not the geometrical, the physical optics. Okay, the physical optics. So we just see the same type of the pattern. Okay, when we have the visible light coming from here and then passing to the buzzer lead here, so we can see the bright fringe and the dark fringe, the bright fringe and the dark fringe, etc. So the same go for the wave of the electron, right? We can see the bright and the dark here. Okay, but one thing that you need to keep in mind is that the bright fringe in this case, right, the bright fringe in this case is going to be the position where we can find more electrons. Okay, so here let's say that, okay, similar to the bright fringe. Okay, it's what is to be the most, okay, probable position to find okay, I don't have space. Let me move here. Wait, oops, sorry. Possible position to find, okay, to find the electrons. Okay, and the dark fringe here is the least probable position to find the electrons. Okay, and that's it. So now you can see that we can see the property of the wave, for the electron, right? So this shows that the electron can behave as a matter wave. Okay, and therefore don't forget that the wavelength of the electron, right, it's just about the wavelength of the X-ray. Okay, another picture is here. So this going to be the comparison between, okay, when we have the X-ray or the electron, right, and hit on the target of the aluminum crystal. Okay, and this can be the diffraction pattern. Okay, so this picture is for okay, is for diffraction by electron, and this from the diffraction by the X-ray. Okay, so let's say that the wavelength of the X-ray and the wavelength of the electron wave are just the same. So now you can see that the diffraction pattern, right, are just the same thing. Okay, so it just emphasizes that the electron can behave as the wave. Okay, electron can behave as the wave as well. Okay, now, okay, what is the application of this wave, right, of this metal wave? So let's see here. Okay, let me move this to this first. Okay, when we talk about the optical microscope, okay, when we talk about the optical microscope, so let's say that we have the object. Okay, the object is here, so it's the one that we just want to see, right? For example, the cell, sperm, or whatever. Okay, and then we have the light source here. Okay, so the light source view the light from the light source, we just pass the lens, so it's called the, what is it called? I think it's called the object lens or not. I'm not sure. Let me see. Okay, I don't know, whatever. It's gonna pass to the lens, right? And then to the specimens or example, and then through the, oh, okay, so this is the object lens. Okay, and then passing through the object lens here, and then to our eyes. Okay, so we're gonna see at this position. Okay, but now the limit of the optical microscope is that we can see the object. Okay, we can see a sample as small as the smallest wavelength of the visible light. Okay, so we know that the smallest wavelength of the visible light is equal to what? Let me move it here. The smallest wavelength of the visible light is equal to about the 350 nanometer, right? So the smallest wavelength of the visible light is just about the 350 nanometer. So it means that the smallest size of the object, or the smallest size of the sample that we can see by this optical microscope, right, it's just about this value, the 350 nanometer. Okay, so this type of the thing is just called the Rayleigh criteria, right? Let me check. I'm not sure. Yeah, correct. Okay, but then what if we just want to see the sample which is smaller and smaller and smaller than this value? So how? Then we can use this thing. It's called the electron microscope. Okay, we can use the electron microscope to solve for this one. So the idea of this electron microscope, right, just the same as the optical microscope. So we have the electron gun here. So the electron gun will emit the electron, right, which is behave as the X-ray. Okay, because the wavelength is just the same as X-ray here. And then it's gonna pass this lens. Okay, but it's called the electromagnetic lens. And then we're gonna have the sample at this position. So now this electron beam will pass, the lens, and then pass the samples, and then pass another lens, right, and then to this screen, and then we can just visual, we can see the sample at here. Okay, so now we said that the wavelength of the X-ray, right, is just about the picometer, on about the 10 to the negative 3 nanometer. Okay, it means that if we use the electron microscope, okay, then we can see a sample on an object which is much less than what we can see from the visible light or the optical microscope here. So this will be the example. Okay, this will be the example of the picture that we can see. Okay, so you can see that actually this fine detail here, right? For example, this fine detail here, something like this, you cannot it cannot be seen using the optical microscope, but it can see it by the electron microscope. Okay, you can see this type of detail, right? This thing, all the hairs here. Okay, so that's going to be the application, of the metal wave or the electron wave. Now then, okay, so now let's look at example. This one. Okay, a beam of electrons is accelerated from rest through the potential difference of the 0.1 kilovolts, okay, and then passes through the thin slit. Okay, so one thing that we can get from this sentence is that because, okay, the electron, let's say that, let's draw the picture. If we have the plate here, okay, so this will be the negative plate, and we have the positive plate here. Okay, but now we say that the potential difference between these two plates, right, equal to the 0.100 kilovolt. Okay, this will be the potential difference between the two plates, and then electron. Okay, so let's say that electron just at rest from this position. Okay, so we have the speed 0 meter per second. Okay, but now the electron will be accelerated, right? Okay, from the left and then to the right page. Okay, so it's gonna follow this path, and also the electron will be speeding up, right? It's gonna speeding up, and then, okay, after here, right, it's gonna pass this hole, let's say the small hole here. Okay, so now with this part we can get that the energy of the electron, let me increase the hole more. Okay, the energy of the electron, right, after passing this hole, right, is going to be equal to of the electron, okay, equal to 0.100 kilo electron volts. Okay, equal to this value 0.100 kilo electron volt. Okay, because this electrical energy, we give all to the electron, right? So it's the energy of the electron equal to this one. So then passing through the thin slit. Okay, so let's assume that we have the thin slit here. Oops. Okay, have the thin slit here, and then we have the screen. Let's say the screen here. Okay, so now I said that the diffracted beam shows is the first diffraction minimum at the 11.5 degree from the original direction of the beam when viewed far from the slit. Okay, so let's say that this is going to be is original part, right? Oops. Okay, so now we expect to see what? We expect to see the high intensity maybe at this position. Okay, and then it will go like this one, and so on. Okay, remember the diffraction pattern from the single slit. Okay, so let me just open it back. Diffraction pattern, right, by the single slit, it's gonna look like this one. Okay, just look like this one. So now I said that the first diffraction minima is at 11.5 degree, right? Then we can have this, okay, let's say this angle, right, this angle to be the 11.5 degree. Okay, so now for the part A, do we need to use relativity formulas? how do we know? So we need to compute for the speed of the electron, right? We need to compute the speed of the electron, and then if the speed of the electron is between this region, then we need to use the relativistic formula. But now if the speed of the electron is beyond this region or the smaller than this value, so we just use the non-relativistic formula, and that's it. Okay, so that's simple. But then how can we find the speed of the electron? Okay, so we said that the energy of the electron, right, equal to this one after passing this plate. Okay, but now the energy of the electron equal to what? Equal to the 1/2 times the mass of the electron and then times the speed square, right? So now we can get that the speed of the electron, okay, is going to be equal to 2 times the 0.100 kilo electron volts, and then over the mass of the electron, and then square root. Okay, and then square root. So now we need to convert everything into the SI unit. Okay, so here we have that equal to 2 and the 0.100, just the same thing. Kilo is what? Kilo is 10 to the 3, right? And electron volt to the joules. 1 electron volt equal to the 1.602 times 10 to the negative 9. Okay, and then over the mass of the electron, which is equal to the 9.109 times 10 to the negative 31 kilogram, right? And then take the square root here. So then finally we can get the speed of the electron to be equal to the 5.93 times 10 to the 6 meter per second. Okay, so let's compare this value with the speed of the light in vacuum. Let's say that if we have the VOC, okay, if we have the VOC, it's going to be equal to what? It's just the 5.93 times 10 to the 6 and then over 299,792,458, right? So it's just about 2%. Okay, it's just about the 0.02, right? Okay, so let's see. V over C is equal to the 0.02. So it means that this value, right, is going to be less than 0.3 times the C. Okay, so in this case, then we can conclude that we may ignore the relativity, and that's it. Okay, now for the part B, how wide is the slit? So we just want to find this size of the slit. So let's say it's be the A. Okay, we just want to find this value. We just want to find the A here. Okay, so then which equation should we use, right? Okay, so now this one is just about the diffraction by the single slit. Okay, let's use this one. A sine theta m equal to the m times the lambda. Okay, let's use this one. A sine theta m equal to the m times the lambda, right? So the A here is going to be, the width of the slit, and the theta m is going to be the diffracted angle, right? And the m is going to be the order of the minima. So in this case, we have the m equal to the 1, right? Because I said that it's with the first diffraction minima here, m equal to 1, and we know the angle already. Okay, we just want to find the A here. Okay, So the problem is we need to find the lambda first. We need to find the wavelength first. Okay, how can we find the wavelength? The wavelength of the electron wave is, okay, we know V, okay, we know V. So if we just want to find the wavelength, we can use this equation, lambda equal to the h over the gamma times the m times the V. But don't forget that in this case the gamma is equal to 1, right? Because the speed is really small compared to the speed of light in vacuum. So then we have that lambda equal to the h and then over the mass times velocity equal to, okay, so now let's just put in number, the 6.626 times 10 to the negative 34, and then over the mass of the electron, right, 9.109 times 10 to the negative 31, and then times the V, okay, the 5.93 times 10 to the 6, okay. So now you can see that, I mean, I just use everything in the SI unit. Then we can get that the lambda is equal to the 0.123 nanometer. Okay, let me just write down as nanometer here. Okay, so now from, okay, the diffraction equation of the single slit, right, of the single slit. Okay, so we have this one, a sine theta equal to the m times the lambda. Then we have that a, okay, equal to the m lambda and then over the sine theta equal to m equal to 1. Let me use lambda as the nanometer here. So we have the 0.123 nanometer and then over the sine of the theta 1, right? In this case, it's just equal to 11.5 degree. So we have 11.5 degree, yeah. So then finally I can get the A to be the 0.616 nanometer, and that's it. Okay, that's be the answers. So one thing that you can see is, okay, let's compare the wavelength of electron and the width of the slit, right? You can see that the width of the slit is about 5 times larger than the wavelength of the electron, right? So that's why I just encountered the diffraction. Okay, so this phenomenon is just the same as, I mean, we observe in the diffraction of the single slit by the visible light, right? Okay.